Alright, so this short video will cover some of the different types of reactions that we're going to encounter in chemistry. And the good thing about this is you've actually already seen a few of them in lab this past week. Alright, so we'll revisit those and then we'll sort of make some connections to what you actually saw in lab. So when it comes to chemical reactions, there are 5 general types that we're going to see. We have combination reactions, which are often referred to as synthesis reactions, and I'll abbreviate the word reaction as rxn. We also have decomposition reactions, and you actually saw both of these in lab this week. We have single replacement we have double replacement reactions, and those two you also actually did this week in lab and you made some observations about those. And the last one are known as combustion reactions, and you didn't actually study this explicitly in lab, but you did take advantage of this when you turned your Bunsen burner on. Okay, so let's take a look at each of these in a little bit more detail. In a combination reaction, that's defined by taking multiple reactants and combining them to form typically one type of product. All right, so the reactants here in this case tend to be generally small molecules or small compounds, and then the product here tends to be bigger because we're just going to stick those smaller reactants together, right? So generally we can say if we have a reactant A combining with reactant B, we just stick them together to make a single product. The example that you did in lab, or that you observed in lab, I did the demo for you, was that we took our magnesium metal and we combined it with oxygen in the air. And if you remember, this little triangle here means that we needed some heat for that to happen. Right? So we combine the magnesium and the oxygen to make our product, magnesium oxide. Right, so essentially what we're doing here is making or synthesizing a new product. So combination reactions are also known as synthesis reactions. The second type of reaction you can think of as being the opposite of synthesis or combination, and that's decomposition. So in this case, we're going to start off with one type of reactant breaking down or decomposes to form multiple, meaning more than one, types of products. Right, so generally we can say if we have our reactant AB, we're just going to split that into 2 or more products. We separate those, we end up making our A and B separately. Right, so we have a couple examples here. You have your mercury oxide breaking down to give you mercury and oxygen, and then that's shown down here in the actual tube itself. So if we have our mercury oxide, we apply a little bit of heat to it. Again, remember the triangle means heat. That breaks down into liquid mercury. And then we see bubbles. In this case, these bubbles represent the gas which is produced, which is oxygen. Another example of a decomposition reaction that may look similar or familiar to you as if you have something like copper 2 sulfate, and that dot 5H2O means it's a special type of ionic compound, so that's called copper 2 sulfate pentahydrate. If we heat that, a little bit of heat, what actually happens is that breaks down into copper 2 sulfate, or solid, and then we also get our 5 water molecules that leave as a gas, right? That's a decomposition reaction, and you actually saw this in lab. All right, the third type of reaction is called a single replacement reaction. These are often referred to as substitution reactions, and in this case, these types of reactions, what's occurring is usually you have one element replacing another in a compound. And typically what we're going to see are either metal, or metal replaces another metal, or a metal replaces hydrogen. Right, so for example, and again, think of it as a substitute or substitution reaction. If we have one element and we have a compound, right, this element A here can come in and kick B out, so now B ends up being on its own, and we make a new combination between A and C. So as a specific example of a single replacement reaction, this one looks or may look familiar to you as something you did in the lab. You had some hydrochloric acid, some HCl, and then you also put into it a strip of zinc metal, which was a solid. And what you actually observe were a bunch of bubbles that were being produced. And we tested those bubbles with the splint, right, if you remember. And then what you observed was the splint actually went out with a pop or a squeak that accompanied it, right? So what's occurring here is our zinc and our HCl react, and the zinc comes in and it kicks the hydrogen out. So we end up making now hydrogen gas, and then the zinc combines with the Cl to make zinc chloride, ZnCl2. Right, so the zinc replaces, or it substitutes, the hydrogen from HCl. So here we have a metal replacing hydrogen from a compound. All right, and you saw a couple other examples of this type of a reaction. The fourth type of a reaction is called a double replacement reaction. Sometimes, I think your book uses this in a couple places. It's also called a metathesis reaction. All right, and what we have happening in this type of reaction is we have two elements that end up swapping places with each other. And in most of the cases, we're going to see metals, other things that are going to swap places with each other. That's not the only instance, but it's the most common example of this double replacement. So for instance, if I have two compounds, AB and CD, right, what can happen is A can come in and it can take the place or replace C, but then C doesn't end up going on its own. It actually comes back and it also replaces, or it takes the place of A. So we make two brand new products now, a new combination, AD and CB, right? So these are our new combinations that are made as those two elements, those two metals, swap places with each other. An example would be if you combined sodium sulfate with barium chloride, right? So what's happening here, we have two ionic compounds. The metal, the sodium from the sodium sulfate comes in and it kicks the barium out, and the barium now goes and it combines with the sulfate. So we end up making barium sulfate, our new combination, and the sodium goes with the chlorine to make sodium chloride. All right, you'll notice that in all of these examples, they're all balanced such that the charges cancel each other out in terms of the chemical formula, but then they're also balanced in terms of these coefficients that we put in to make sure that the chemical equation as a whole is balanced. The fifth type of a reaction is known as a combustion reaction. This is not one that you explicitly saw in lab, but you did make use of it in your Bunsen burner. So in a combustion reaction, what we observe is that typically a carbon containing compound reacts with oxygen to produce carbon dioxide and water vapor, right? So these are gases. And then it also releases energy, right? And that was the most important thing from the Bunsen burner, the energy in the form of heat and the light that you actually saw. So for instance, your Bunsen burner, the fuel there is a combination of two gases, methane and ethane, for instance, and methane has the chemical formula CH4. That was a gas in your Bunsen burner. It reacted with oxygen in the air, and then that produced our CO2. We also got H2O, and then we can, because energy was also produced, we can also write energy in as a product. All right, and then you would need to go through and balance that equation. I'm not going to balance it for you. That's a good practice question to go through and balance. So in a combustion reaction, right, we end up producing CO2, H2O, and then a bunch of energy that we take advantage of. So this would be an example of when there's a lot of oxygen available, right? So we call that a complete combustion. Lots of O2 available, and you were able to adjust your Bunsen burner to move the barrel up or down to allow lots and lots of oxygen to come in. And as I had demonstrated to you in lab, if you turn the barrel the other way from the Bunsen burner, you actually saw the flame change to a yellow billowy flame, right? So that happens because there ends up being incomplete combustion, because in that case, what happens is there is not enough oxygen to completely react with specifically the carbon in your reactant, right? And what that means then is that the products are going to be different, and specifically it also produces CO, which is carbon monoxide, which, as you probably know, is very poisonous. All right, so when there's not enough oxygen to completely react with the carbon in our fuel, then we refer to that as incomplete combustion. And one of the additional products that we get is CO, right? So that's why, for example, you don't want to have your grill operating in an enclosed space, right? You grill outdoors. You don't necessarily want to grill inside where there's not enough oxygen available to completely burn the fuel, because you end up producing some of the poisonous carbon monoxide. All right, and then the last type, which wasn't actually on our original list of 5, but it is something that you saw in lab, were our ionic equations. And then in your ionic equations, you can we're going to apply these to our substances that are in the aqueous or AQ phase or physical state. And when you have something that's aqueous, what that means is that it's dissolved in water. And what's going to happen is that substance is actually going to dissociate or split into the ions that actually make up that compound. So for instance, if you have something like sodium sulfate Na2 SO4, and that's aqueous, right? All we're going to be doing here is just taking that and breaking it down into its its component ions, which is just the opposite of putting ions together to make your ionic compounds. Right, so the way that this works is the subscript here on the sodium actually becomes the coefficient in front of it when it breaks down. So the sodium sulfate is made up of sodium ions, Na, and we also have the sulfate ions. Right, specifically now, this is going to have 2 sodiums and there's 1 sulfate in this compound. So the subscript here of 2 becomes the coefficient in front of our sodium. Remember, sodium is Na+, that's Aq. And then we also have our sulfate, right? You have to recognize this now as your polyatomic ion, and that has a 2- charge, and that's Aq, aqueous, right? So your ionic compound here, that's Aq or aqueous, splits into its components. We have sodium and we have the sulfate. The subscript on the sodium becomes a coefficient on the sodium when it breaks apart.